little acronym thingies. So the forecaster wades through what the computer spits out and what they get from the National Center for Environmental Prediction. And actually, I took a small group of students to Chicago one year, and we went and visited the news station there and met with a meteorologist. And you really got a sense for he could basically supersede or put his own twist on the forecast that he receives based upon what he knows about Chicago, and the time of year and everything. So that's pretty cool, I think. And ultimately, the forecaster will say what the forecast is going to be, and he'll share it with the public. Okay. So I've got some bloopers down here, and I haven't previewed them all, so I hope they're okay. So, we looked at ensemble forecasting, okay? But you know what? Ensemble forecasting, you kind of needed it's numerical weather forecasting on steroids, basically, right? Ensemble forecasting. And some of these also you need a computer too. So persistence forecasting, if somebody is persistent, that means they keep on. So persistence forecasting goes out on a limb and says, well, if it didn't rain today, it won't rain tomorrow. So that's basically persistence forecasting. And I've read that certain parts of the world, like I guess Hawaii, they get kind of the same type of weather all the time. So that works. Climatological forecasting, you use climate data. So like I say in my slides, we could say December. I can bet you I can forecast the weather next December 2016. I can say the temperatures are going to be between 30 and I don't know, maybe something lower like 20. And so that's just based upon the climate. So the thing about White Christmas, that's always every year. It's like, are you going to have a White Christmas or not? Well, you can use climate data and come up with the probability of having a White Christmas in these areas. So, yeah. Forecasting for next December. And then there's this analog method of forecasting. So if somebody has come up with an analogous situation, that means it's a situation very similar to this one, analogous situation. These two situations are very similar. So in an analog method, what you do is, I think you need a computer again, basically you look at what the conditions are today, the conditions of the atmosphere, and you find historically a day that matched today, and then you march it forward, so whatever that weather happened after that day, that's what tomorrow's forecast is going to be. Analog method. Trend forecasting, it uses, for instance, we are in the Ferrel cell, and we know that our weather patterns generally come from the west. So we can kind of use general things like that to see a trend and think, well, that weather out west is going to be what we have tomorrow. Nowcasting is kind of a subset of trend forecasting, but nowcasting is more immediate than trend forecasting. So it's kind of, you use common sense in trend forecasting, I think. So now on to a little more about satellites. So satellites can give us some information, somewhat limited because it's definitely indirect information that we can feed into our models and spit out a forecast. So I want to talk about two types of satellites, and they differ by how far they are above the Earth when they orbit the Earth, and where they orbit the Earth. So we start with, this is a figure of polar orbiting satellites. Polar orbiting operational environmental satellites. See, they're the same thing. Let's see, I swapped out my figure. Okay, so polar orbit. Now, the reason it's polar is it basically goes from pole to pole. So like it kind of goes like this, and then it scoots over a little bit at longitude, although the Earth is rotating, so, and then it goes like this, and it goes like this, and it kind of covers a different line of longitude as it goes around. This is the closer of the two scenarios, and like the slide says, it's great for getting information about the poles, but it's really kind of a hit and miss as the Earth spins. Okay, I don't know where that's going to be. It takes 100, is it 100 minutes? Yeah, about 100 minutes, about an hour and a half to go around once. If you've ever like dabbled with finding the Hubble Space Telescope or, the Hubble Space Telescope, it actually has this sort of orbit around the Earth. Of course, it's not worried about the Earth, it's worried about the stars, okay? So that is, they're called POES, Polar Orbiting Operational Environmental Satellites. So the other one is the GOES. And in this one, they're called Geostationary Operational Environmental Satellites. So I'm going to underline the word stationary, geostationary. So the deal there is they basically hover. The Earth spins on its axis. Well, two things. They are kind of near the equator, in the vicinity of the equator, and they just sit at one position all the time. But they can't just sit at, if they want to hover over a position as the Earth spins, they have to keep up with the Earth spinning. So that's kind of how that goes. If you look at this figure and the previous figure, you'll see that this figure has, and I noticed this just recently, here's the satellite, here's the GOES satellite, and here is the area that it covers. Okay, it's not very good for the poles, but it's great for the mid-latitudes. It covers a pretty big area. You can't see detail because it's way up there. It's farther from the Earth's surface, but you can get a sense for hurricanes and that sort of thing. So I'm going to go back right quick. So this one, if I circle the area, it's like this right here. So it's a smaller area because it's closer to the Earth's surface. Cool. I went ahead and we'll see if it'll take me out there. Your textbook talks about this GOES-R, and it caught my attention because it's like in 2016, this new type of satellite, next generation of satellites, should be out there. And just today, April 14th, this article was published. Okay, so this is our new generation of these geostationary orbit satellites. This caught my eye too. You know, it's got a video. I'm not going to play. I think I'll push that out there on Twitter. But check this out. The weather imaging capabilities of this new model are like going from a black and white television to an HD TV. So I thought that's pretty cool. Geeks. But, so I think I read it a few times that it looks like August they're hoping to launch it. We'll see. Anyway. Back to the show. Okay. So those satellites, whether it's the polar one or the geostationary one, okay, they send us images, and we have an option of images. But the images basically are gathered as the satellites do these scans. And it takes, I've read, 15 to 30 minutes to do a scan. So wherever it is, it basically scans, takes a picture, composite picture, and it scans according to, or it can set different wavelengths that it's gathering information from. You know, we talked about information, we talked about energy, about radiation. Radiation can be transmitted, absorbed, or reflected, or scattered. And so that's what it's actually looking for, that information coming from the Earth. So we'll look to see how each one of these types, there's 3 types, how they can each be helpful. The first one is visible light images. It took me not that long to figure out this the one if the satellite's looking in visible wavelengths, it can only see the Earth at the daytime side of the Earth. So if you guys are the sun, okay, and this is the Earth and you guys are the sun, over here, if I'm looking at the visible wavelength, I can't see anything. I just thought that was interesting. But it's good for clouds. Infrared, you should hopefully kind of think thermal energy. So it can switch wavelengths, and instead of getting visible, it can get heat signatures. This is good for sensing. Remember the other day we talked about cloud tops being very cold? Basically, you have a thunderstorm cloud that's punching through the atmosphere and cooling as it goes. So very cold cloud tops indicate unstable situations. If it's nice and warm and toasty, actually it's probably sensing the Earth. So the last one is you can change the wavelength, and actually you can get water vapor that's in the atmosphere. So that's pretty cool. So we're going to look at these examples of these coming up. But if you know where the water vapor is, you can go ahead and send that information along. You should expect pretty high dew point temperatures if you have a lot of water vapor. So predicting fog and that sort of thing. So on these water vapor images, when you see milky white, that means it's high in water vapor. When you see dark, that means it's dry. Okay, so starting with the visible light images. So I've got several satellite images, and many of them actually on July 15th, 2011. I'm going to kind of show you individually, but so this is the daytime side of the Earth, and you can kind of see these clouds here. Okay, clouds. This right here, I don't think this is I think this must be a different date, because I don't know if you can kind of see those cute little multiple cells. Okay, but those would be the overshooting tops. But they said it's centered on Iowa. I don't know, because when I look at Iowa, I don't see overshooting tops like that. So, okay. The note here is that actually here, this was heavy precipitation. Bunch of cloud cover. Makes sense. So switching wavelengths from visible to infrared, a little bit longer wavelength. So your author's gone ahead and has some kind of coded this. So where you see ones, this is thermal imagery. Where you see ones, there's no clouds. You're actually getting it nice and toasty because of no clouds there. Where you see twos, they're low clouds. And where you see threes, they are middle clouds. And where you see fours, actually those would be the cooler cloud tops. So this over here is a false image. Right here and here, those are the cold regions. All right, last one is water vapor. So this is on the same day, and again, where you see it's milky white, the whiter it is, the more water vapor there is. The dark, it's dry. So here are those for July 15th, 2011. The visible, so if we kind of just kind of pick on here, Minnesota and, is that Michigan? Wisconsin. What's this one? Help me out. So this is Michigan. So this is Wisconsin. So Minnesota and Wisconsin, thermal imagery, Minnesota and Wisconsin, water vapor. Not so surprising. Okay. So when you put forward what the condition of the atmosphere is going to be, you can either go qualitative or quantitative. And if you're familiar with these words, qualitative means, well, start with quantitative. Quantitative means numbers. So your quantitative forecasts actually have something measurable. Your qualitative forecasts are something potentially a little more vague. Partly cloudy in the morning, followed by clearing. That's an example of qualitative forecast. So precipitation forecasts, I've actually got a couple slides on this. Precipitation is one of the few where the National Weather Service will go out on a limb and give you amounts, give you some numerical quantitative information. So the X's are where they're higher precipitation. The numbers are in inches of precipitation. They call these a quantitative precipitation forecast, a QPF. The other thing the National Weather Service will put out is the POP, stands for probability of precipitation. So this piqued my interest, so I went ahead and chased it down and put it on a slide for us. So you may have heard this before, like if they say there's a 20% chance of precipitation, what does that mean? Well, it means that they have taken some number that they call the confidence level, that precipitation will occur anywhere, okay, in the forecast area, times the area that they think that the precipitation is going to occur. So they take those two times each other. So for instance, I have an example down here from your textbook. If they're 50% confidence that somewhere in this forecast area it's going to get rain, okay, that's their C term. 0.5 is their C term. And if when that rain event happens, they think that 80% of the area, the forecast area, is likely to get precipitation. So take the confidence, which is 0.5, times the percent of area that's likely to be affected, 0.8, and multiply it by 100%, and they get 40%. Probability of precipitation. So these were probability of precipitation forecasts for the same time. All right. Long-range forecasts, as defined by, well, the most common long-range forecasts are those 3-month forecasts that they put out. And they're put out by the Climatology Prediction Center, the CPC. And not so surprising, they use climate data, and they do use a model that suits them. And to me, if you've ever, and I grab one every year, picked up a farmer's almanac, that's what these are, I think, or a version of this. So when you're looking that far out, one of the things you're going to see is, notice I have down here, especially unreliable. It's definitely not as reliable as your 2-day forecast or something like that. The transition months, when you're going from one season to another, apparently it's not very reliable. These long-term forecasts, they can look at big things like El Nino, La Nina, which cycle are we in? Okay. So these would be the 3-month forecasts from September to November for 2011. The first one on the left is temperature, and on the right is precipitation. The equal chance means that it's equal chance to be warmer or colder, or wetter or drier. And like I said, Farmer's Almanac definitely has these in them each year. So this caught my eye too. Look at that chick sitting next to all those computers. Okay, and this makes sense. So basically what that is showing you a station, an advanced weather interactive processing system, where she has at her fingertips access to multiple models and an assortment of initial conditions, observational data. Makes sense. And then she can kind of do her magic. Okay, so why weather forecasts go wrong? and I'm sure you get this. This makes sense. One of them is the models aren't entirely correct, and it's hard to mimic Mother Nature. The second one there, I think I mentioned before. I think I mentioned that one too. The computers can't crunch all the numbers that you feed them. There is uncertainty in these initial conditions, and that leads to kind of an assortment of outcomes. If you know there's this tolerance in all measurements. There are holes in available data. So, like I mentioned during the smoothing that you can kind of estimate between points. But like, if we want to know what the condition of the atmosphere is out here in the middle of the ocean, oceans are notorious for there's nobody out there. Okay, there are planes flying back and forth. You know, we might have a miscellaneous station out there, but those holes mean that we have holes in our initial conditions. So yep, I wish I had a job where I could be so wrong, so a lot of time to keep my job. Some people do. So with regard to being accurate, the farther out ones are less accurate. The closer in ones are more accurate. So when we talk about forecast skill is basically how better are you at anticipating what tomorrow will bring than just climatological data. Like, what are we, the middle to end of April. So I predict tomorrow will be, you know, somewhere between, you know, 60 and 40, you know. Can you do better than that? That's skill. Then I thought I would leave these in my slides this semester. I didn't necessarily find them in your textbook, but let's see. So forecast quality can deal with qualitative forecasts. If you have numbers, you can actually do forecast accuracy. And if something is biased, that means it's slanted one way or the other. And so you want to be real careful if you're always overestimate the temperature, the maximum temperature, or you always underestimate. Oops, sorry, Earth. I wanted to go to this last website. I found this last year. So it actually, remember we talked about the different models? Okay, so here, well, I guess this wouldn't be models, this would be just different group. So it's not for Keokuk, but it says how accurate, which had that, let's see, weather online, 64%. So if you're wondering, you know how forecasts vary just a little bit? If you're wondering who's the most accurate, this is kind of an up-to-date, who's the most accurate. So it's a thought. I know a lot of people do AccuWeather. Dark skies, I do that for astronomy. But anyway, persistence forecasting, we talked about that. Yeah, I don't think so. So, okay, very good. Well, we'll go ahead.